In 2010, a researcher at Yahoo named Chudnovsky did something strange. He took a 1,000 machine cluster, ran it for 23 days, and computed exactly one number, just one, the 2-quadrillionth binary digit of pi, 2 times 10 to the 15th. He found that it was 0. Now here's the thing, he did not compute the first digit of pi. He did not compute the second digit. He did not compute any of the digits between the first and the 2-quadrillionth. Just that one specific digit by itself, far out in the expansion. This shouldn't be possible. We have been computing pi since Archimedes. Every algorithm we have for it works the same way. Start at the beginning, grind out digits one by one, get further and further. The Chudnovsky algorithm is the fastest way we know to compute pi sequentially, and it still has to compute all the digits up to the one you want. So how did somebody jump straight to digit number 2 quadrillion? The answer is a formula that was discovered in the fall of 1995. It was found by accident by a computer and proven by hand only afterwards. Today we're going to look at exactly what it is, why it works, and why nobody knew it could exist until a Canadian mathematician fed pi into the right algorithm. Take any number you can think of. The square root of 2, Euler's constant, pi itself. Most of these numbers are irrational. Their decimal expansions go on forever and never repeat. The standard way to compute the nth digit of an irrational number is to compute the entire number to n digits of precision. There's no shortcut, because every digit depends on the cumulative arithmetic that came before it. If you want to know what's in the millionth decimal place of pi, you need to do approximately 1,000,000 digits of work. If you want the trillionth, you need 1,000,000,000,000 digits of work. If you want the quadrillionth, well, that's why you'd need 1,000 machine cluster running for 23 days. This isn't a quirk of bad algorithms. It's a structural fact. Pi is built up by summing infinite series, and you have to add up enough terms to get the precision right. The Madhava series, Newton's series, Machine's formula, Ramanujan series, Chudnovsky series, they all converge to pi at different speeds, but they all need full precision arithmetic to extract any specific digit. So in 1995, when somebody announced you could compute the nth digit of pi without computing the previous n-1 digits, the natural reaction was disbelief. Here's a fact most people don't know. For rational numbers, fractions like 1/7, you actually can extract any digit you want without computing the previous ones. Take 1/7, its decimal expansion is 0.142857, repeating forever. Suppose you want the millionth digit. Here's how you get it. Take 10 to the millionth power, divide by 7, take the fractional part, multiply by 10, take the floor. That's your digit. The whole computation reduces to one quantity, the remainder when 10 to the millionth power is divided by 7, and that remainder is fast to compute. There's an algorithm called modular exponentiation that lets you compute 10 to the n, modulo any number, in roughly the logarithm of n basic operations. For n equals 1,000,000, that's about 20 multiplications. For n equals 1,000,000,000, it's 40. For any n at all, it's tiny. The trick is repeated squaring. You compute 10 squared, then 10 to the 4th, then 10 to the 8th, then 16th, all modulo 7. 20 steps gets you 10 to the million. Then you assemble these from the binary representation of n. So for rationals, digit extraction is essentially free. The hard case is irrationals, and that's where pi comes in. Simon Plouffe was a Canadian mathematician working at Simon Fraser University in 1995. He was not a celebrity. He had no PhD. He had spent years building something called the inverse symbolic calculator, a tool that took numerical decimal expansions as input and tried to identify them as known mathematical constants. His colleagues at Simon Fraser, the Borwein brothers, had recently helped develop an algorithm called PSLQ, created by Hellman Ferguson and David Bailey in 1992. PSLQ is an integer relation finder. You give it a list of real numbers, and it tries to find a small integer linear combination of them that equals 0. It's a generalized version of the Euclidean algorithm extended to many dimensions. In the autumn of 1995, Plouffe set up an experiment. He took pi, computed to a few hundred digits of precision, and asked PSLQ a question. Could pi be written as an integer combination of polylogarithm-style sums that look like 1 over 16 to the k, divided by linear functions of k? PSLQ ran. It returned a vector of integers, specifically 4, 0, 0, -2, -1, -1, 0, 0. Plouffe didn't know what to do with it at first. The Borweins did. That vector was a formula nobody had ever derived from theory. Here it is. Pi equals the sum, from k equals 0 to infinity, of 1 over 16 to the k times a bracket. Inside the bracket, 4 divided by 8k plus 1, minus 2 divided by 8k plus 4, minus 1 divided by 8k plus 5, minus 1 divided by 8k plus 6. Let me check it. First term, k equals 0. The bracket is 4 over 1, minus 2 over 4, minus 1 over 5, minus 1 over 6. That's 4, minus 0.5, minus 0.2, minus 0.1666. Sum 3.1333. Already close to pi. Now the second term, k equals 1. The bracket is 4 over 9, minus 2 over 12, minus 1 over 13, minus 1 over 14. That's about 0.129. Divide by 16. About 0.008. Add to the first term, 3.1414. We've got 4 correct decimal digits of pi from 2 terms of the series. By the 5th or 6th term, you have 6 digits. By the 10th, you have 12 digits. The series converges fast, about 1 1/4 decimal digits per term. But this is just an ordinary convergent series for pi. Many such series exist. What makes this one extraordinary is the 16 to the k denominator. That structure is the key to everything that follows. Here's the move. Suppose you want hex digit number n of pi. The way to get it, compute pi, multiply by 16 to the power n minus 1, take the fractional part, multiply by 16, take the floor. That's the digit at position n in base 16. So we need the fractional part of 16 to the n minus 1 times pi. Substitute the formula for pi. Each term of the series gets multiplied by 16 to the n minus 1. The 16 to the k in the denominator combines with this. You get 16 to the n minus 1 minus k multiplied by the bracket. Now split the sum into 2 pieces. The terms where k is less than n, and the terms where k is greater than or equal to n. The second piece, k greater than n, has 16 raised to a negative power. These terms decay like 1/16, 1 over 256, 1 over 4000. After a couple dozen terms, the sum is precise to many digits. Cheap. The first piece, k less than n, has 16 raised to a non-negative power. Each term is a positive integer divided by a small integer like 8k plus 1. Take the fractional part. The integer divided by integer becomes its remainder, divided by the small integer. So we need 16 to the n minus 1 minus k, modulo 8k plus j. And that's exactly what modular exponentiation gives us, in O of log n operations. Per term, with n terms total. The whole digit extraction takes about n log² n bit operations, and the working memory is only log n bits. The space efficiency is what matters. You can compute the trillionth bit of pi without storing a trillion digits. The algorithm depends entirely on one fact. You can compute 16 to the m modulo q in roughly the logarithm of m operations. The technique is called square and multiply. Suppose m is 1 trillion. Write m in binary. It's about 40 bits long. Now compute, in sequence, 16 to the 1 mod q, 16 to the 2 mod q, 16 to the 4 mod q, 16 to the 8, 16 to the 16, all the way up to 16 to the 2 to the 40th power. Each step is just one squaring of the previous result, then taking the remainder mod q. 40 squarings. After that, you assemble 16 to the m by multiplying together exactly the powers of 2 that appear in m's binary expansion. For m a trillion, that's about 40 multiplications. Each squaring or multiplication keeps the numbers bounded by q², then reduces by q. Q in our case is at most 8n plus 6, a small number, so the arithmetic operates on tiny integers. The whole modular exponentiation is microseconds, and the algorithm calls it n times once per term in the series. That's why the trillionth hex digit of pi takes about a few seconds on a laptop, not 3 years. The formula gives pi in base 16. That's the 16 to the k structure. Equivalently, base 2, every hex digit unpacks into 4 bits, so we can extract any binary digit of pi we want. Cheap and direct. But not base 10. The formula has no power of 10 in it. If you wanted the trillionth decimal digit, this approach gives you nothing. You'd have to extract enough hex digits to convert, and converting requires all the digits up to that point. That's the deep limitation. Could there be a similar formula for base 10? In 2004, 3 mathematicians, Jonathan Borwein, David Borwein, and William Galway, proved that no formula of this exact shape exists for pi in any non-binary base. Specifically, no degree 1 machine-type formula. This doesn't rule out radically different digit extraction methods. In 2022, Plouffe himself published an alternative base 10 algorithm for pi, but it requires computing the previous decimal digits. It's not a true spigot. So the gap remains. Pi is spigot-friendly in base 2 and base 16, and nowhere else as far as anyone knows. There may be a deep reason, there may not. It's an open problem. Let's actually compute a digit. Suppose you want hex digit number 100. For each j in the set 1, 4, 5, 6, sum from k equals 0 to 99, the value 16 to the 99 minus k, modulo 8k plus j, divided by 8k plus j. Then add a small tail of about 20 more terms with negative powers of 16. Form the combination 4s1 minus 2s4 minus s5 minus s6. Take the fractional part, multiply by 16, floor. That integer is the 100th hex digit of pi. The whole algorithm runs in milliseconds. The memory used is a few hundred bytes. No infinite precision arithmetic, no big integers, no large internal state, just modular remainders, and a final fixed point sum. You can run this for any n, million, billion, trillion, quadrillion. The cost grows almost linearly. The memory stays constant. In 1997, 2 years after the original formula, Fabrice Bellard found an improved version. Same idea, different polylog combination. Denominator 2 to the 10th instead of 16, about 43% faster per digit. Bellard used his own formula to compute the billionth binary digit of pi on a workstation. Then came pi hex. Colin Percival organized a distributed computing project with hundreds of volunteers across the world. By the end of 2000, they had computed the quadrillionth binary digit of pi. The answer is 0. In 2010, Chudnovsky pushed it to the 2-quadrillionth bit on a 1,000-machine Yahoo cluster, also 0. In 2018, the 100-quadrillionth hex digit was computed on an Intel Xeon Phi cluster. The technique extends. PSLQ, the algorithm Plouffe used to find the formula in the first place, has gone on to find closed-form expressions for the Riemann zeta function at 3 and 5, for Catalan's constant, for Madelung sums, for Feynman diagram amplitudes. PSLQ was named one of the top 10 algorithms of the 20th century. A whole subfield opened up. Experimental mathematics, using computers not just to verify proofs, but to discover the identities themselves.